Hi everyone. In this video, we are going to look at physical realism. We will be looking at how to create game objects with realistic physics models, and also how we can simulate aspects of reality in order to make them behave more realistically. So that's what we will be looking at when we discuss physical realism. These are the sections that we will cover during the course of this video. There are 16 subheadings that we will walk through. So as an introduction to physical realism, physics engines simulate physics, Newtonian physics, for models in a particular scene. So usually we use separate libraries for this modeling purpose. And a real-time simulation of movement and interaction can be captured in this way of modeling. So the game basically provides us with physical info about the world. For example, the size of the world, the mass, center of gravity, forces, etc. The physics engine in general simulates movement, collisions based on the information that is provided. So in the next slides, we will be looking at how collision detection happens. I mean, how it's modeled, how movement is done, etc. So when we talk about existing physics engines, it's quite difficult to implement a fully complete physics engine from scratch. I mean, we can do smaller parts such as collision detection, etc. But developing the complete engine is a complex task. The core component of these is a program called a solver. So solving Newtonian equations, then the precision in mathematics and programming algorithms, etc., is integrated into this core program called the solver. Then a common to use existing physics engine, as in the engines which are usually used when it comes to this type of modeling, are some of the things that are listed here. There are other things as well, but these are some of the common engines that we could use. So there are a couple of things which we will look at during the course of physical realism slides. Rigid body simulations is one of those things. We will not extensively discuss rigid body simulations in this slide set, in this video, because there's a separate video for rigid body simulations. Just like that, there's a separate video for soft body simulations, etc. So physics engines simulate rigid bodies and soft bodies. Okay, we call them bodies, not models. Basically, they are models, but we usually go with the first term when it comes to the physics engine. Rigid body simulation is quite straightforward because usually handling deformation is difficult when it comes to soft body simulation. The collision volume, which we will look at in the next slides, there's something called collision volume. It is usually a simplification of the visual model. For example, a car may use a box as a volume, or character as a set of boxes and cylinders. Okay, we need to use certain visual models in order to depict the objects in our physics engine. And also we can connect these together for more complex models. And rigid bodies are usually defined by their collision volume or the shape. Now let's look at collision primitives. So we can choose the physics body shape from a given set of primitives. So the primitives usually are a box or a cuboid or a sphere, a cone, cylinder, etc. So out of these simple primitives, we can choose the physics body shape of the body that we are going to model. So each primitive is treated as a precise mathematical object rather than a polygon. This improves the speed of the engine and produces more accurate simulation and smoother results. Why? Because we are treating each object as where we are treating each primitive as a mathematical object. Therefore, it improves the accuracy. However, these simple primitives could mean inaccurate collisions. Those could occur. Now, when it comes to collision volumes, say what if no suitable collision shape for a model or precise collisions are required? So if there's no such requirement, then we can simply use the primitives, or we can use the boundary of the polygonal mesh of a model as the collision shape, which we call a convex hull. So using this convex hull, we can increase the time and the memory required for the physics simulation. And at the same time, it will increase the accuracy of the collision as well. But the thing is, these details could bring unwanted side effects, such as, say, for example, a polygonal cylinder might not roll as smoothly as a mathematical one because of the flat sides. So that's the advantage of using a mathematical object to represent the primitives rather than just going with a polygonal shape. So as you can see, here we have used collision primitives, just like we discussed before. We are using simple primitives. We said these are simple primitives: box, sphere, cone, cylinder, and all. So these simple primitives are used to come up with a convex hull like this. We have built the convex hull using these collision primitives. So what's a convex hull? A convex hull is the boundary of a polygonal mesh of the model. How did we build that? We did that using the primitives, the collision primitives. Okay, now let's look at the static physical properties. When it comes to any type of object, any body, it has certain static properties. Just like we have studied so far, the body has a mass. It has a center of gravity, moments of inertia, elasticity, friction. All of these things are properties, physical properties of a body. These are what we actually use when we apply Newton's laws of motion and to calculate the effect of interactions with other physics bodies. That's how we represent collisions or movement or whatever we want to do in our physics, whatever we want to do in our game engine. We do it by applying the Newton's laws of motion to show what happens between bodies. So for that, The physical properties of each body are necessary. The mass, gravity, moments of inertia, which means how mass is spread around the body. So if the mass is focused at the center of gravity, then we can easily rotate it around the center. But if it is more spread out, then it's harder to rotate it. So these properties are used. So those are static properties. Now, when we come to the dynamic properties of a physical body, then the position, the orientation, linear velocity, angular velocity. We will be looking at all of these in the upcoming slides. Then forces, torque, impulses, everything, all of these things are coming under the dynamic properties of a physics engine body. So together, this forms the current state of the physics world. The static properties and the dynamic properties together form the current state of the physics world. The initial state is set by the game. Then state dynamically updates, and it's being updated by the physics engine. Now let's look at the relationships of these physical properties which we discussed a minute ago. So using these only, we can connect the bodies together to show what happens in this game engine. So these connections usually represent joints. A joint meaning, look at the third bullet point, a joint is defined by the models involved in the joint, degrees of freedom, as in linear motion, angular motion, then stiffness. So joint is defined by these three things. What are the models involved in it, the bodies involved in it, degrees of freedom, and then the stiffness. Several joints can be used for more complexity. For example, you can use machines, chains, and there's something called the ragdoll, which is the set of primitives connected like a human body. Several joints can be used. Now let's look at the relationships of these physical properties that we discussed a minute ago. Using these, the bodies can be connected together. So these connections usually represent joints. What is a joint? Well, a joint is defined by three things. First one, the models involved in the joint. Second, degrees of freedom, linear or angular motion. And the third one is the stiffness of the body. So the models in the body, the degree of the freedom, and the stiffness of the body are what defines a joint, which is a connection of bodies. Then several joints can be used together for more complex objects. For example, chains, machines, etc. So there's this ragdoll, which is a set of primitives connected to look like a human body. We know what primitives are, which we discussed, collision primitives. So you use these primitives to develop an object which looks like a human body. Let me show that to you. So this is an example of that. So here we have used the set of primitives to develop an object that resembles a human body. Let's go back to the slide set. Okay, now when we are looking at initializing a physics simulation, when you want to initialize a simulation, we need to create a rigid body in the physics engine for each model in our scenario. For this, we need to choose the proper shapes, the proper collision shapes. So using the proper shapes, we are going to create rigid bodies for the models in our scene. Then we need to define the static properties for each body. You remember we discussed static properties and dynamic properties. So each body should have its static properties, mass, center of gravity, and the other things that we discussed under static properties. Then we need to define any joints. Why do we need joints? We need them to connect bodies together. So we need to define them as well. After that, we need to initialize the dynamic properties. Where the body should initially be, the initial position. The velocity of this body. Is it a linear motion? Is it an angular motion? So using these dynamic properties and the static properties, we need to define each of these for the bodies that we model in our environment. And then we need to define the joints that connect the bodies together. So when we look at game physics in general, computer animation physics, or in general, game physics, involves the introduction of the laws of physics into a game engine. What we basically do is Newton's laws of motion are introduced into a game engine through game physics. So we see game objects reacting to simulation similar to real objects in the real world. And game physics is quite important to us because it gives more and more realism to the game. It makes it look realistic. So these are some of the game engines which we looked at earlier as well that have been developed. The physics engines, examples for them. Okay. Now we have game physics. We have physics engines developed using that. Now, what is the player's expectation? People expect office applications to fail, but they don't expect 100% uptime from business websites. What we are willing to tolerate when we work is quite different than what we are willing to tolerate when we play a game. Okay, so when it comes to the efficiency, complexity and computability are the two concepts that are not normally taught. But game programmers need to consider efficiency in everything that they do. It's a must. Because studies have found out that if a player has to wait for more than 30 seconds for levels to load in a game, their review of that game will be reduced. Because of this, even though complexity and computability are concepts which are not looked into much, efficiency is a must. It affects the reviews that the game would get. Okay, now game mathematics, just like game physics, game mathematics refers to both areas of geometry, calculus, trigonometry, etc. At the same time, specialized areas such as vectors, matrices, and all. So you know that we looked at mathematics for games in a previous video, mathematics for games, physics for games, etc. So that's what we're talking about here. You have the general mathematics areas, plus you have certain specialized areas as well. Right, then we have collision detection. So we spoke of collision primitives. Figuring out if two objects are touching is a common problem in a game. Even in the games that you have played, you must have come across places where two objects collide with each other. So these, I mean, capturing these collisions is a problem. So to do this, we have two basic techniques. The first one is the overlap testing technique, which detects whether a collision has already occurred or not. Other one is intersection testing, where it predicts whether a collision will occur in the future. So these are the two techniques that we have. Overlap, which checks if it has happened already, and intersection, which checks if it will happen in the future. Okay, so like we said, this is not an easy task. Detecting a collision is not easy. Why? Because geometry is complex, objects move fast, and also there can be many objects. Okay. So just like we said, these two techniques will be used in this circumstance. Now look at overlap testing. So this is the most common technique used in games. And it's more erroneous. It causes more error than the intersection testing concept. So for every step, we update all the objects, test the objects to see if they have overlapped. And if they have, then we make adjustments or corrections. That is how we do it in overlap testing. So this is good for simple volumes like boxes, spheres, etc. But for complex objects, polygonal models, this is not a very good method to use. So the results, useful results that we can detect of a collision is normal vector, collision normal vector, which we can use for future physics actions as well. And the other thing is the time that the collision took place. These are useful results for future reference. Then where we come to symbol overlap. So here, testing easiest example is now we come to simple overlap testing. So the easiest example of simple overlap test is of a particle interacting with a square. This will require 4 logical tests when it comes to a 2D game to detect the interaction. So depending on the type of the game, the order of these tests can have an effect on the efficiency of this detection. So now let's look at the collision time when it comes to overlap testing. This is calculated by moving objects back in time until right before the collision. You move the object back until you come to right before the collision. Okay, so let's look at this diagram and see what happens. So at the very first part, we have done the initial overlap test. Then what do? We need to move backwards or forwards so that we come to the position where right before the collision. So after the initial overlap over here, we go forward by 1/2, by half a step, which is called a bisection. We move forward, then we come backward by 1/4 of a distance. Then again, we go forward by 1/8. Then again by 1/16, and then we come backwards again by 1/32. So likewise, we go forward and come backwards by half a step each time. Each time we take half a step. We were here, then we took half a step. We took half a step backwards. Likewise, each time we take a bisection, and somehow we come close enough. We get within the delta distance, which means close enough to the point which is right before the collision. Okay. So in practice, this usually takes about 5 iterations. Then we can get pretty close to the point where we want to be. Point right before the collision. So this is how the overlap testing works. This is how the collision is detected once it has happened using the overlap testing. So there are certain limitations in overlap testing. If the object moves too fast, overlap testing cannot catch the time slice because obviously we are going back and forth by half a step. So if it moves too fast, then it's hard for us to catch the point which is right before the collision. So the possible solutions for this limitation is that you design constraints on speed of the object. Which is to say, you say, okay, the fastest object moves a very small distance than the thinnest object. But it might not be practical for all the games. The other thing is you reduce the simulation step size. You can try different step sizes for different objects. But it could add overhead when it comes to the computation. Okay, how do we test, intersection testing? So what happens in intersection testing is it predicts future collisions. So when the collision is predicted through this algorithm, what happens is it moves simulation to time of collision. Then it will resolve the collision. And then it will simulate the remaining time. Once it is predicted, it will move the simulation to that place, point of collision, then resolve it. Then the remaining time step will be simulated. It's depicted here. So here you are at TO. You move to the collision time, T1, resolve it, and the rest of the time, the remaining time is simulated. So this is for additional knowledge. You can see here. So you have T0 to T1. Q1 goes from, Q goes from Q1 to Q2. Then you have again T0 to T1. So if T is in 0 to 1, then there is a collision that can happen at this point. But if the distance is large enough, then the collision will not occur over here. So when it comes to bounding volumes, this is a simple geometric shape that completely encapsulates the objects. And the testing is cheap in these. So the bounding volumes that we usually use are spheres, boxes, etc. For complex objects, we can fit several bounding volumes. For example, a human character. So boxes around the torso and limbs, then spheres for the head, just like what we saw in the example that I showed. So if we have a complex object, then we can come up with several bounding boxes. Here again, for your knowledge purposes, we have the Minkowski sum. So what basically happens is you take the sum of two volumes to create a new volume. So you have X and Y. You take the sum of these two volumes to create a new volume together. So what you basically do is you sweep the center of X over Y. You can see it in this example as well. Then again, using the same, if you want to test if a single point in X will collide, then what you do in the Minkowski sum is that you take the center of the sphere at time 0 and time 1, take the two centers, you draw a line between them. If the line intersects the new volume, then there's a collision. If this line intersects the new volume, then there's a collision. So this is the Minkowski sum is also for additional knowledge for you. These come under complex geometry. Okay, now we come to Newton's laws of motion. Now we come to Newton's laws of motion. So we'll be talking about inertia, F equals ma, equal and opposite reaction. We'll be looking at these. So how do Newton's laws of motion apply? Velocity remains a constant unless acted on by a force. So unless if an object, unless if a force is applied on an object, well, the velocity of this object should remain the same. And then the object accelerates, according to F equals ma, this object should accelerate if an interaction between two objects affect either one. And the other thing is that so how do these Newton's laws of motion apply? Well, the velocity remains the same unless a force is applied to an object. If there's no force applied, if there's no additional extra force applied on the object, then its velocity has to remain the same. And then the acceleration of an object happens according to F equals ma. The next thing is that interactions between the objects should produce an equal and opposite reaction. So these applications are necessary for us. And the other thing is how they don't apply. Velocities that give, that reduce over time give better numerical stability. Objects are often moved instantaneously. That doesn't happen. That doesn't apply. Many interactions are one-sided. There's no reason to simulate the other side. That's not the case either. You need to, interactions between objects should affect both the objects similarly. Okay, so Newton game dynamics is actually a physics engine for realistically simulating rigid bodies in games. In contrast to the other physics engines, Newton game dynamics goes for accuracy over speed. So its core program, which is the solver, is deterministic, and it's not based on traditional iterative methods. So we can handle higher mass ratios, and the simulation is very robust, but it's a bit slower than the other engines. But Newton 2.0 has greatly improved the simulation speed. Okay, so we discussed about rigid bodies, an object that moves but does not change shape or the mass property. Define how these objects are affected by force. So there's a mass, center of gravity, moments of inertia when it comes to an object. Then what's a simulation? We want to write a simulation describing the motions of the given set of objects. And then we integrate the equations of motion between these objects. So as we spoke about before, there are several data types when it comes to the mathematics of this. There are data types which we come across. We have scalars, vectors, matrix, quaternions, Euler angles, etc. So these were actually discussed on the mathematics for games part. So these are necessary for us when it comes to game physics. So we talked about what vectors is. It represents the location, and scalars are numbers. They represent a characteristic such as a mass. Quaternions, well, they contain an orientation, which means they can, which means they can rotate vectors, and also interpretability is smooth. Then we have particles. First we will look at the particles which are reduced from rigid bodies. So particles differ in that they don't have an orientation or that they have a position. So certain particles have an orientation, certain particles have a position. When it comes to Euler angles, they're the ones who were developed to produce, to replace vectors. When we look at scalars, well, these represent characteristics such as mass. Then quaternions, they contain an orientation and they are mostly used in modern game engines. And then going to particles, well, rigid body particles differ in two ways. Well, one is they can have an orientation and the other is that they have a position. Then when we look at scalars, well, this represents simple characteristics such as mass. Quaternions, well, they have an orientation and they are mostly used in modern games. Particles, well, these are reduced form of rigid bodies and they differ in two ways. One is having an orientation and the other is having a position. Then when it comes to Euler angles, well, these were what were developed to replace quaternions. And then we have the rotation matrix. It's another alternative to quaternions. Then we have tensors. It's an algebraic object. It describes the relationship between objects related to a vector space. Finally, we have rigid bodies, which we discussed before as well, and we will be discussing in a separate slide set. They have a position and an orientation and movements. Then moments of inertia, well, this is the rotational equivalent to mass, describes how hard it is to rotate an object, and it depends on the axis of rotation. Therefore, it can be considered as a tensor, sorry. Therefore, it can be considered as a tensor.